For today, the lecture topic will be on neural networks. Okay, so this is the final kind of machine learning model that we are going to cover in this course. Okay, but it is also a very important one, right? So, what are neural networks? Okay, neural networks have or deep learning, which is a term that people use to also describe neural networks. Have gotten a lot of hype in recent years, right? So you probably have heard a lot about many of the feats that they can perform. So in many areas, they have outperformed many traditional machine learning methodologies. So what you see on the right here is basically the performance of various machine learning algorithms on the ImageNet dataset. In other words, the dataset where you develop machine learning algorithms to recognize what is in an image, like what is whether it's an image of a cat or a dog or a car or airplane and so on and so forth. And what you see is that starting from about the 2010s onwards, neural networks have essentially dominated the scene, right? So all this, you see this AlexNet, CNN, SPPNet. Whenever you see a net at the end, that is a form of neural network. Okay, so obviously they are a lot more sophisticated than just a simple feed-forward neural network, but they are fundamentally based on roughly the same architecture. Okay, so when we talk about things like AlphaGo, where you have this machine beating the world's best Go player for the first time, the underlying machine learning architecture is a neural network. Okay. Now, what is a neural network or artificial neural network, right? An artificial neural network is essentially a learning algorithm that is very, very loosely based on the structure of the mammalian brain. Okay. You will also hear other ways of referring to neural networks. So for example, if you hear the term multi-layer perceptron or MLP, that refers to an artificial neural network. Okay. So why have artificial neural networks gotten so much attention in recent years, right? And it really is because of this universal approximation theorem. Okay, so a very, very long time ago, okay, so back in the 1950s or so, someone has already mathematically proven that a feed-forward neural network with just a single hidden layer and containing a finite number of neurons can actually approximate continuous functions under mild assumptions of the activation function. Okay, so I'm going to talk about what the activation function is in a little bit, but what this simply means is that neural networks are universal approximators. Okay, it means that it doesn't matter what the relationship between the input and output is. Okay, they can artificial neural network can represent any such relationship with a finite number of neurons with a single hidden layer, right? So obviously, with more hidden layers, the performance can be better. And of course, when we say a finite number of neurons, it can also be a very, very large number of neurons. But by and large, this property of neural networks is an extremely powerful one. Okay, so how does the neurons in an actual human brain work? Okay, so this is actually the structure of a neuron in the human brain. Okay, so you basically have one neuron on one side, and basically your neuron will actually receive an input, okay, from somewhere, right? Let's say your hand touches a hot item, right? And what happens is that then the signal then gets conducted through this axon, and on the other end you have another neuron which then receives that input from the other neuron. Okay, now whenever we talk about a neuron in the human brain, there are certain properties of that signal transmission process that you need to understand. Okay,
So what happens in a neuron is that basically once it takes an input signal, and the input signal is then processed through the neuron, and it is only when the input signal exceeds a certain threshold, so in other words when the neuron is activated, that signal get passed on to the next neuron. Okay, so it is this activation process that is particularly important and unique to the brain. Okay, so how do we go about representing this in machine learning architecture? Okay, it turns out very simply, right? So this is basically a very simple schematic of artificial neural network. Typically what you have on one end are basically your input neurons. Okay, so these basically take in your input signals, okay, or features. Okay, and what you have in between the input and output are basically what are called hidden layers. Okay, so these hidden layers essentially comprises of multiple layers of neurons. Okay, and when you have a fully connected neural network, you essentially every single neuron in each layer is connected to every other neuron in the next layer and the layer before it. Okay, so this is why it's called a fully connected neural network. Okay, so at the end you basically have an output layer. Okay, and that output layer consists of output neurons, and eventually those take in signals from the final hidden layer and then convert it into into an output. Okay, so this can be either a single scalar output, it can also be a multiple outputs of different values. Okay, now what is exactly going on within each of these neurons? All right, so remember again, I bring you back to the neuron in the human brain. You basically have an input, and then only when the input exceeds a certain threshold, then you pass on the signal to the next layer. Okay, so to model this, basically we have a structure like this, right? So each neuron is basically just this linear function, right? So you basically take in the signal x1, x2, and x3. You have coefficients alpha m here, denoted as alpha m here, that is being multiplied by all these inputs, and then you add in some constant term, right? So this is basically just a linear function of the input. Okay, and what you have here is this sigma function. This sigma function is what is known as a activation function, right? So an activation function basically only transmit the output when the output exceeds a certain level. Okay, so there are certain common choices for this activation function. Okay, examples include the rectified linear unit, the sigmoid function, and the soft plus, and so on and so forth. Okay, I'm going to go show you what those functions look like in the next slide. All right. So these are basically the different activation functions that I just talked about. So on the left here, you basically have your rectified linear unit represented by the red line. It is a very, very simple function. Okay, the rectified linear unit simply states that, well, when the signal is less than 0, I transmit a 0. So I don't actually transmit negative numbers. Okay, and only when the signal is greater than 0, I transmit the signal itself. So in other words, I just take in the linear combination of the outputs, and then I just pass it on, transmit it directly to the next layer. Okay. The soft plus function is a little bit different. It is actually a continuous function that works this way. It is still fairly similar. So basically, when you actually have signal that are below a certain threshold, you can see that gets attenuated very quickly. While as you increase, as your signal strength increases, you progressively reaches asymptote value of basically the value itself. Okay, you can imagine that as e to the power of x becomes very, very large, this one factor is actually quite insignificant. So the log of e to the power of x is basically just x itself. Okay, so
So basically these two activation functions performs quite similarly. The advantage of using something like the soft plus is, of course, you don't actually have this ugly discontinuity in the derivative at 0. So this is actually a continuous derivative, which in some instances is actually better. Okay. Similarly, for the sigmoid function, this actually performs somewhat differently from your soft plus and ReLU. When your signal is greater than 0, you keep transmitting the value until you reach a certain threshold. Sorry about that. Beyond which it basically just peters out, and when the signal is negative, you basically get truncated to 0 in itself. Okay, so this is basically what the sigmoid function looks like, right? So you can imagine this essentially simulates the neuron in your human brain in some approximate fashion, right? So in other words, you are taking a set of signals, you are transforming in some way using a linear combination of the input signals, and then only when the signal is larger than some value, you then pass it on to the next layer. Okay. Now, whenever we talk about fitting a neural network model, okay, what we mean is essentially just fitting the alphas in the linear function, right? So in other words, you can see that each neuron has its own alphas, so the coefficients of the linear function, okay? So you can imagine however many neurons you have is however many alphas that you have, right? So to actually fit those alpha values, which are called weights, okay, you essentially use an algorithm called backpropagation, which was developed by Hinton and collaborators. Okay, so backpropagation is effectively just a form of gradient descent. So in other words, you are trying to minimize your loss function with respect to your weights alpha. Okay. Loss functions are typically not very different from what you would use in other machine learning models. You will use the square error for regression, or you will use something like cross entropy for your classification problems. Okay. To avoid overfitting, very typically you also apply some form of regularization. So we have covered this time and again, right? So the way that you do this is that you have a penalty term that try to penalize models that are too complex, right? And how do you know, how do you measure, say, the complexity in a neural network? Essentially, that is measured by the number of alpha values that is greater than, that are non-zero, and of course, the magnitude of the alphas themselves, right? So typically, the regularization that we use in neural networks is some form of weight decay. So in essence, the term is related to the summation of the square of all the weights. Okay, so that is the regularization penalty term. So there are a few decisions for neural networks. Okay, so similarly to your random forest ensemble learning models and decision trees, unlike your linear regression model where essentially you have no adjustable parameters, and ridge regression and lasso regression where you basically have just one adjustable parameters, similar to the trees, you actually have a number of parameter decisions you have to make for your neural networks. Okay, so the main one is of course the number of hidden layers and number of hidden units. Okay, so in other words, how do I know for this architecture, do I need 3 layers, 2 layers, 1 layer, or 10 layers, right? So that's basically one question you have to figure out. And even after I decide how many layers I need, how do I know, do I need 10 neurons in this layer, or 5 neurons in this layer, and 2 neurons in this layer, right? So all these are the parameters that you have to adjust when you are looking on when you're working on neural networks. Okay, so generally the recommendation is to err on the side of having too many hidden layers rather than too few. Okay, so especially if the relationship between your input and output is highly non-linear,
you do need that flexibility to capture that non-linearity in relationship, okay? Now, even if you start with too many hidden units, you can always shrink the weights down to 0 using regularization techniques, okay? So that's why it's actually always better to start with a neural network that is maybe a bit too big for the problem that you are doing, and then you then shrink down the weights to 0, okay? Now, whenever we fit artificial neural networks, the learning rate is the key parameter that you also need to adjust. Essentially, the learning rate controls the rate of gradient descent, right? So how fast do I go down the gradient of decreasing loss with the weights, okay? Now, a very high learning rate reduces your training time, right? But it can also result in decreased accuracy, right? So the state of the art is actually to use an adaptive learning rate, right? So where maybe at the start of your training process, the artificial neural network actually uses a much higher learning rate, and as we get closer and closer to our optimal model, you actually decreases the learning rate, okay? Now, it should be noted that the error function is non-convex and contains many multiple minima. So in other words, depending on how you initialize the weights, you may actually get a different final solution. Okay, so there is no one right model in a way. Okay, so you typically would start from a number of random initial configurations, and then you choose the solution with the least penalized error. Okay, so there's no way to really predict how the weights, what kind of solution you will get depending on the initial condition, right? Now, an alternative that some people do use is to use ensemble learning, right? So remember, when we talk about ensemble learning, we are essentially averaging the predictions from multiple models. So we have talk about ensemble learning mostly in the context of decision trees, but there's really nothing preventing you from using multiple artificial neural networks to do your ensemble, okay? Now, this is actually an area where we do need to talk a little bit about the software packages that are used for neural networks, okay? So scikit-learn itself does have an implementation of a simple multi-layer perceptron or feed-forward neural network. So for this course, we are going to just use this. The main reason is that I don't want to be introducing to you many different Python packages, and each of them have a different API, right? With the scikit-learn one, you will see that the API is actually quite similar to what you have been using throughout this course, okay? Now, however, if you are really into serious work with artificial neural networks, and I would be surprised that you aren't if you are actually going to work a lot on application of machine learning to whatever problem you have in your lab, there are alternative software packages that offer many more features, and they are sometimes a lot more efficient, right? Most of these packages are also not limited to artificial neural networks, although artificial neural networks are the most common use case, right? So two packages that I'm sure you have heard about. One is called TensorFlow. That is basically an open source package by Google. It is very powerful, it's very efficient, but the learning curve is very steep, okay? It usually takes you some time to figure out how to actually configure a neural network and to train it using TensorFlow. But once you do it, it is basically one of the most powerful packages you can use, and they also have versions of TensorFlow that are designed to run on different hardware. So for example, you have TensorFlow that are customized for mobile applications and that sort of thing, okay? PyTorch is the one that a lot of scientists like yourself use. So this is an open source package by Facebook.
It is equally powerful as TensorFlow. The learning curve also tends to be quite steep, but I would argue it's probably not as steep as TensorFlow. All right, at least at the very least, with my personal experience, I find PyTorch a lot easier to learn than TensorFlow. Okay. All right. Just to show you the difference between the scikit-learn version and the TensorFlow version. So to use the neural network implementation in scikit-learn that is under the neural network package, there's something called the MLP regressor. And how you initialize the MLP regressor or MLP classifier is that you specify the hidden layer sizes. You have to specify some alpha parameter, which is your weight decay penalty. And then you also have to specify the number of iteration, the maximum number of iterations you want to allow the fit to go to. Okay, so just like your ensemble learning models, theoretically the fit can go on forever, right? So you do need some kind of stopping criteria to say, well, I'm going to stop my training at this point, right? There is an initial learning rate. This basically tells you what kind of learning rate you are going to start with, but this learning rate is adaptive. In other words, it will be adjusted as your training proceeds, right? Other than that, the API is exactly similar to what you have used for the rest of your scikit-learn machine learning packages. So you just call fit, you call score, you can use your grid search CV with all of these, okay? Now, to actually do it with TensorFlow, you can see here is basically what the TensorFlow version of this MLP regressor looks like. You actually have to specify an input layer, and you have to tell the input layer exactly what the shape of your input is, okay? You then follow by a dense layer, and you have to specify, well, I need 5 neurons in that in the first hidden layer, and the activation function I want to use is ReLU, and this dense layer is the input layer then connects to this dense layer. Okay, dense just means it's a fully connected neural network. Okay, then the next hidden layer has 3 neurons. Similarly, is also using the ReLU activation function, and then that is connected to your previous hidden layer. And finally, you have an output layer that is connected to your second hidden layer. Okay, and then you get initialize the model. You have to specify the optimizer with the learning rate. Here we use what is called the Adam optimizer. And then you have to compile the model before you finally do the fit. And you have to specify the number of epochs, which is basically the number of iterations, and what is the size of the batches that you're going to use in terms of the training data to fit the model. Okay, so lots and lots of configuration options, and very, very powerful. You can optimize for fast convergence and model performance, but again, very, very steep learning curve, right? You can imagine this is much harder to figure out how to do compared to, just one line over here, right? Okay, so let me go to the example in our lecture. Okay, so I am going to do this, and I'm going to show you the documentation first of the neural network. Okay, so you can see that scikit-learn itself actually does have a very, very good documentation page on the different kind of machine learning models. So for example, they have this entire section on neural network based models. They also actually warn that the implementation is actually not for large scale applications, right? So for example, scikit-learn has no GPU support, right? So you do need to be very aware of this, right? For the kind of problems that our class is working on, you are not going to need GPU support. But whenever we talk about most other machine learning problems that you are going to encounter in the literature or when you're doing your own research,
once you actually have any sizable data set, you typically would want to have GPU-based implementations, okay? So you can see here, this is basically how the the neural network works. They talk about the MLP classifier, the scikit-learn neural network package. So I'm going to click on this just to show you what it looks like. I'm going to come back to that. So you see that under the neural network, they actually only have three different classes. The classifier, the regressor, and this Bernoulli RBM, which I'm restricted Boltzmann machine, which I'm not going to talk about. Okay, but you can actually click on this to look at what are the parameters. So you can see that the main thing that you want to specify for sure is the hidden layer sizes. You typically also want to think about what kind of activation function you want to use. So they actually have your rectified linear unit, they have the hyperbolic tangent function, there's a logistic function, and you can also use the identity. In other words, identity just means that there is no activation at all. Sorry. Oh, you're still seeing the, sorry, I forgot about that. Oh, okay. Oops. Okay, thank you. Thank you for letting me know. All right. I forgot that I need to switch. Okay, so let me go back a little bit, right? So in scikit-learn, as I mentioned, there are a lot of sections on the models themselves. These are actually very, very useful for you to read because they actually gives you a summary of what the principles behind each of these models and how they work, okay? And they have some tips on practically how to use them. As I mentioned, they are very explicit that scikit-learn does not offer GPU support, which is fine for the purposes of this course because I deliberately chose questions that you may not need, you shouldn't be needing GPU to fit the models. But if you are working with any large-scale data set, you probably want to choose a package that actually has GPU support, okay? So things like TensorFlow and PyTorch, definitely they have GPU support built in, okay? So under the scikit-learn neural network package, there are three different kinds of classes, the classifier, the regressor, and of course this Bernoulli restricted Boltzmann machine, which we are not going to go into. If you look at the regressor, as I showed you before, one of the primary things that you need to input is basically what is your hidden layer. So this is basically a list of numbers, right? So this basically says that I have just one hidden layer and that hidden layer has 100 neurons, okay? So that's basically the default. The likelihood is that this is not going to be sufficient for what you're doing, okay? You have to play around with this thing. The activation function, by the default, it is the rectified linear unit, but they also have other options like the hyperbolic tangent and the logistic function. Identity is actually a special one. This actually means that there is no activation at all, right? So typically this is never used, okay? So this is just for you to test, all right? You can see that there's the solver is here being used is the Adam optimizer. This is a very, very typical choice. And the alpha parameter, you can actually read about it. This is basically the L2 regularization term. This basically is the weight decay term that we just talked about, right? Now, in terms of learning rate, they actually have different types of learning rate. The default is the constant one. In other words, there is no change in the learning rate. You just set it as the initialization of the initial learning rate. You can also set it to adaptive. So what this does is that after you will basically keep decreasing the learning rate after you actually if your training loss stops decreasing. Okay, so this is pretty useful, right? And of course there are all the other terms. The other thing that I want to highlight is that if you intend to play with the multi-layer perceptron in your lab number 3, you typically have to set the max iterations, okay?
200 is almost always never enough for you to converge your neural network properly, right? I usually set it to like 10,000 or more than that. Sorry, give me a second. Give me a, I need to respond to this. Okay. All right. So this is basically the documentation. So refer to this when you are playing around with it in your lab. Okay. So just to show you, this is basically our lecture notebook. Okay. So we are going to work on the exact same problem that we talked about previously, which is a smaller version of your lab number 2. We basically are trying to do a prediction of the metal insulator data set using a neural network. Okay, so so as you can see, let's say the top part is basically similar to your lab number 2. In other words, we are creating a classification problem where you basically have metals versus insulators, and you have the feature set which are based on the atomic radius, atomic weight, and the electronegativity. Okay. Now, when we talk about when we are playing around with the neural network, as I mentioned, we can start with the MLP classifier. You can also use grid search CV with the neural network. Okay. With grid search CV, what you would do is that you specify all the other parameters. So you see that I specify the alpha, the random state, and the initial learning rate. I didn't specify the hidden layer sizes. Okay, and the reason is because I'm going to use grid search CV to find what's the best hidden layer configuration for my artificial neural network, right? So you can see that this is basically all the ones that I'm trying. One is basically just a single layer of 3 neurons, single layer of 5 neurons, single layers of 7 neurons, 2 layers, one with 5 neurons and the next layer 3 neurons, 2 layers 7 and 5, and 3 layers 7, 5, 3. Okay. I'm going to use the accuracy as my scoring function, and I'm going to run my grid search CV. You can see that actually when you look at the fitting, you saw some error message, warning messages that the maximum iterations has reached, and so that means that probably is not converged, right? So you would typically have to set this to say something like 1,000 or even 10,000. Okay, and this is the way that I'm going to run this. I'm going to let it run for a while, and I'm going to show you the results. Okay, so this is basically we can also play around with the value of alpha. Let's say if I choose a certain hidden layer size, and then I look at different values of alpha from 10 to the power minus 6 to 10 to the power minus 1. I can look at what's the effect on the accuracy with different alpha values. Now, here is pretty interesting. You basically see that we don't actually get much difference in performance depending on our alpha value, right? With the regression task, similarly, you can see that, well, you can play around with different layer sizes. So, and you can see that, well, it turns out that 5.3 seems to give me the best score. Okay, so the best performing model seems to be the 5.3 model. All right, and that actually sorry, the three hidden layer model, sorry, over here. And you can basically also play around with different values of alpha and hidden layers. Okay, so this is basically just an example of how you go about fitting a MLP regressor on an example problem. Okay, so I suggest you use this when you're working on your lab number 3. Okay, now I also provided you with a TensorFlow example. This is basically almost the same. I'm not going to go through it quite simply because other than the nomenclature, okay, or the semantics of the code. Everything else is actually exactly the same as what you have with the scikit-learn version. Okay. All right. Let me share my slides again. Okay. So any questions on the simple artificial neural network before I continue? All right, if not, let me continue on. So in this course, obviously, I'm giving you a very high level overview of neural networks. Okay, I'm because the general idea is that we are not trying to make this into a full-fledged computer science, data science course, right? In some instances, just talking about neural networks alone can be just one quarter or one semester course in itself, right? Especially if we are going to cover things like their how you properly fit them, what's the algorithm that you use, and what they can and cannot do, and so on and so forth. But nevertheless, it is important for you to understand that beyond just your standard feed-forward neural network, there are some variations that have been developed for some of the applications, common applications that you see out there in the public domain. Okay, so the first kind of variation is what I call convolutional neural networks. Okay, so this is actually a very, very interesting class. What convolutional neural networks were originally designed to solve one very specific problem, which is translational invariance. Okay, this is especially important in image processing applications, right? So you can imagine that a picture of a cat is a cat, regardless of whether that cat is sitting in the bottom left corner of your image or in the center of your image or the top right of your image. Okay, so this is what is meant by translational invariance, right? So we don't really care about translation of the image. The content is actually independent of that translation, right? So convolutional neural networks are designed in such a way to achieve that translational invariance. Okay. Similarly, in material science, we actually have many instances where this kind of translational invariance is important, right? So for example, whenever we model crystal structures with periodic boundary conditions, we also have translational invariance too, right? Just shifting the atoms by a constant vector has no effect on the properties of that material itself. Okay, so that is why you can see that the convolutional neural networks actually would be potentially interesting for such applications. There are also what are called recurrent neural networks. Okay, so in this case, the connections between the nodes actually form a directed graph along a temporal sequence, right? So this allows the model to model temporal dynamic behavior, and it can also handle variable length sequences of inputs. Okay, so a classic example of where recurrent neural networks can be useful are things like handwriting recognition or speech recognition, right? So for instance, I noticed that one of you have enabled the closed captioning in the Zoom application. Okay, so obviously behind that closed captioning is essentially a machine learning model that is translating what I'm saying into actual words. Okay, and typically you need some form of temporal behavior to model that. So for example, if I say I am a professor, right? The fact that I'm saying I have said I before allows the model to interpret when I say am, what word am I referring to much better. So in other words, there is a certain kind of relationship between words in different languages. Okay, so being able to model that temporal relationship between words is actually extremely important for doing something like speech recognition. Okay. The same thing goes for your autocorrect sequence in your phones. Okay, so you notice that when you type a sequence of a sentence, even though sometimes you have written many different mistakes when you type, the autocorrect actually somehow magically works. Okay, the reason is because the autocorrect actually understands that, well, you are most likely going trying to type this because that's the most likely sequence of the most likely sentence structure that is in the English language. Okay. All right. So I want to show you how neural networks have been applied to material science, especially. Okay. So one big area where neural networks have been applied to is for interatomic potential development. Okay. So for those of you who have taken modeling of materials before, so for instance, if you are taking the course by Todd Pascal on where you do molecular dynamic simulations of materials using a force field or interatomic potential, that is what I'm referring to, right? So traditionally, when people talk about force fields, they usually are based on some very rigid functional form, and people just tweak the various parameters until they get some approximate behavior that is in line with what they observe experimentally. Today, there is actually a much better way of fitting interatomic potentials or force fields, right? So one example of a machine learning interatomic potential is what I call the Baylor-Parinello, the neural network potential, okay, or which are based on basically what I call the Baylor-Parinello atom symmetry functions. Okay, so the way that this works is basically they use symmetry functions to represent the atomic local environments. Okay, so for example, to represent the distances between atoms, you have this radial functions. Okay, which basically is just exponent of the distance between the two atoms. Okay, and you basically sum this across all the different atoms with this cutoff function. Then you also need to represent what are the angles between the bonds of the atoms. So here you see that there's this cosine term of the angles. Again, there's also this weight that is related to the distances between the atoms. Okay, so the way that the neural network potential works is that you basically uses all these as basis functions, and you use an artificial neural network to basically map the symmetry functions to the final energy of the system. Okay, so people have used neural network developed neural network potentials for many different systems, including things like silicon, titanium oxide, also molecular systems like water, metal organic frameworks, if that's your thing, zinc oxide, and so on and so forth. Okay, so there are just too many to list. Okay, so just to show you the example for silicon, so this is something that all of you intuitively understand, right? So the way that this works is, of course, you take the Cartesian coordinates of your silicon system, you map them onto your atom-centered symmetry function, and for each of these atom-centered symmetry functions, you basically have an artificial neural network that map it to the energy. Okay, and this set of atomic energies then get summed up to the total energy of the system. Okay, and basically what you do is that you use your standard backpropagation algorithm to basically figure out what are the weights that should be in all these neural networks. Okay, just to show you that it works very well. Okay, so the black line is what you get with density functional theory, which is a first principles based approach. So you should think of this as basically the gold standard, at least in this instance. Okay, so it's definitely not perfect, but it is the best you can do here. And the rest are all basically different types of interatomic potentials that people have fitted over the years. Okay, the Tursov potential, for example, is this yellow line. This is a very classic potential that people use for silicon in the literature. And the red line is basically the neural network potential that was fitted to this silicon system. And you can see, impressive, right? The neural network potential that is fitted for silicon here is very, very close to the black line. So in other words, you actually get extremely good agreement on the radial distribution function, at least with the neural network potential for silicon, okay? And this is not a fluke, right? So even though I just showed you for silicon, but people have consistently been able to do this for many, many different materials and for many, many different properties, okay? So I would say that by far fitting interdynamic potentials or force fields is one of the great success stories of the application of machine learning models in material science, okay? Yes, more or less transformed the way that we have we are fitting interdynamic potentials, right? This is another example. So here is a slightly different system, which is the lithium silicon system. So for those of you who do not know, silicon is a very interesting anode material for lithium ion batteries, okay? So unlike the graphite that is used for used in your lithium ion batteries today, a lot of people actually, a lot of studies are actually being done on using silicon, which actually can hold a lot more lithium per unit weight and volume compared to graphite, right? And so in order for people to study that, one of the things that they need to figure out is basically when you put lithium into silicon, what are the different kind of phases of lithium and silicon, what are the different phases of the lithium silicon alloys that are going to be formed during this lithiation process, right? And to do that, there's this work that basically fitted neural network potential for the lithium silicon system, and then they use this interdynamic potential to basically compute the phase diagram using thousands and thousands of calculations of different lithium silicon configurations, okay? So this is not something you can do with your standard first principles theory quite easily, all right? Because their first principles DFT calculations are very, very expensive, right? This is an example from my work, okay? So I will say that this is something that you probably want to keep in mind because your final lab is going to be somewhat related to this. It's not exactly the same, right? So one of the kind of materials that we were interested in was garnets and perovskite crystals, which have a certain formula, okay? And we wanted to be able to predict the formation energies of garnets and perovskite crystals just from a very simple set of inputs. For example, the Pauling electronegativity and the ionic radii. And what we found was that essentially just with a few hidden layers, we can actually get very, very good prediction of the formation energies. In fact, less than 10 MeV per atom accuracy, which is pretty good. Which will then allow us to basically explore a much broader universe of garnets and perovskite crystals, okay? Now, just a final example. So for example, I also talk about other kinds of neural networks, like for example, convolutional neural networks. This is work from Professor Ken Vecchio also in the nano engineering department. Here is actually a different kind, an experimental kind of problem. They basically have an electron diffraction image that you see over here, okay? And what they wanted to do was to develop a machine learning algorithm that can figure out what kind of crystal system is this electron diffraction pattern which crystal system, what crystal system does the material actually belongs to from its electron diffraction pattern, okay? And they basically found that with a convolutional neural network, they are able to get more than 90% accuracy, okay? All right, that's pretty much it for the neural networks. Any questions before I continue on?